I am going to go ahead and introduce our next speaker. James Epperson is an associate professor of mathematics at the University of Texas at Arlington. Dr. Epperson has worked extensively with emerging scholars programs for over 20 years and currently directs the Arlington-ESP program, which is funded in part by an NSF Science Talent Expansion Program. He recently was not only inducted into UT Arlington's Academy of Distinguished Teaching Professors, but also awarded the 2012 Texas Section MAA Award for Distinguished College or University Teaching of Mathematics. His talk today will focus on the links among inquiry-based learning, metacognition, and emerging scholars programs. So I introduce Dr. Epperson.
I'd like to thank the organizers for inviting me to the conference. This is my first RL Moore conference, and although I'm not new to the Moore method, my undergraduate topology courses and my graduate topology courses were all taught in the Moore method. But I guess, you know, as a Tejano and somebody who went to graduate school in Austin, that was unavoidable. I've used many of the ideas from the Moore method in my teaching throughout the years, and but without further ado, I'll get to our focus for today, and that's the role of inquiry-based learning and metacognition in emerging scholars programs. A little bit of an outline of what I'm going to do today. I'm going to first talk briefly about about emerging scholars programs. So we have the setting. We'll talk about inquiry-based learning and how it relates to ESPs. A little bit about metacognition in ESPs, data from our local project, and also some final thoughts. Emerging scholars programs, or Treisman-style programs, are grounded in early Treisman's research from the 1970s. That research sought to try to find an explanation for the differences in mathematics achievement between African American and Chinese American students in calculus at Berkeley. After a long ethnographic study, very interesting study that Uri undertook, he found that the biggest factor that explained the difference in performance between the two groups was that it was rested in the beliefs about what studying math meant. What he found were that the barriers to success was working in isolation and also compartmentalizing their lives into sort of social and academic components. So the group that was doing poorly the students tended to work in isolation, and they tended to compartmentalize their life. You know, they had the social group of friends and the academic group of friends. I think, as we've seen in many of the talks over the last day and a half, or day and a morning, that one of the components or one of the key things from inquiry-based learning is that working in isolation isn't a good thing. There's time for individual work, but there's also time for collaboration, and that it's as part of becoming socialized into the mathematical community. It is very much part of an inquiry-based approach. Some central themes for ESP programs are collaboration, community, and challenge, mathematical challenge. In collaboration, the students spend the majority of their time working in groups in these sessions. This enables them to form friendships around their shared academic pursuits. It also allows them to have time to investigate problems in a manner that they may or may not be accustomed to. The community aspect of ESPs tries to foster or facilitates this creation of an academic community that also overlaps with their social peer group. Mathematical challenge, the students are given an opportunity to explore more challenging aspects of mathematics. And so that for certain populations, that will reinforce their views of themselves as capable of high academic achievement, but also very empowering to do mathematics in that way. And I think that's what we've seen in other talks at this conference about inquiry-based learning. So what do model programs feature in ESP? One is they feature increased class time, more personal contact with peers and graduate students and faculty. They foster a student community. focus on challenging work. That's sort of a really big core central piece of an Emerging Scholars Program. And then there's this structural piece of specialized academic advising to help students navigate the university. In terms of inquiry-based learning, yesterday at the presentation by Tom and Vilma, they were talking about concerns of instructors in using inquiry-based learning, or what was reported to them. And one was, of course, this time crunch, that one feels that perhaps spending time on inquiry, you then have your timeline becomes compressed or lengthened, and you need to fit in a whole bunch of material in there. Well, ESP programs in some sense avoid that, in that they have increased class time to be able to do this. So it's kind of working the world at both ends. So many Emerging Scholars Programs, the immediate goal is to increase the number of students excelling in calculus and pre-calculus. There are Emerging Scholars Programs that have been developed in chemistry and physics and other areas of science, but I'm going to focus today, of course, on calculus and pre-calculus. The original goals were rested in increasing the numbers of freshman students excelling in calculus and pre-calculus, and that certainly is one of the goals of my own program at UT Arlington. But many students can come into this program, and the focus is being able to excel and increase the number of students excelling in calculus and pre-calculus. So a little bit of the structure. ESP intensive sections meet for a total of 4 to 6 hours per week outside of, or in addition to, lecture and regular lab. And so a typical program would have 2 hours of discussion. Students in regular lecture would go 2 hours of discussion. ESP students might go to 4 to 6 hours additional. ESP sections, when they meet at 2-hour time blocks, so that students do have the time to investigate complicated or more involved tasks and to engage in inquiry. So some of the key components of inquiry-based learning that I gleaned from the Academy of Inquiry-Based Learning site. In mathematics, they said that kind of the essence was to engage in sense-making activities. Also, key components were to deep engagement in rich mathematical activities, and then opportunities to collaborate with peers. Well, as we saw, the key components for emerging scholars of the community aspect, collaboration, also the deep engagement in mathematical activities. Well, the focus, of course, on an emerging scholars program won't work as an emerging scholars program if you don't have those challenging mathematical activities. And students have opportunities to engage in sense making. Now, from the science education literature, this continuum in science I thought was applicable to, particularly because this is a continuum that was developed in elementary school. But given yesterday's opening talk, where some of the more methods was applied to high school students or high school classroom, I think that we hear inquiry, the word inquiry, both in mathematics and, of course, in science. This inquiry continuum starts out with this confirmation inquiry, where students confirm known results. Structured inquiry, where you have teacher-presented and teacher-scaffolded questions. So those kinds of questions do appear on emerging scholars tasks in an emerging scholars program. It's a sort of a structured, the teacher knows kind of where they want the students to go. Guided inquiry, where the teacher still presents the questions, but then the students select the approach and the procedures. And then, of course, we go to the open inquiry, where the questions are student formulated and the student designs and selects the procedures. In terms of metacognition, sort of a simple way of thinking about metacognition is thinking about one's thinking, being able to think about your own thinking. We want students also to be self-aware as a problem solver, to have self-regulation, be able to monitor and control one's mental processing, and also to be able to have this idea of self-assessment, be able to accurately judge their level of learning. Many times students have issues in succeeding in calculus because they can't really gauge before they go into an exam how well they actually understand the material. So in the collaborative setting, students do have an opportunity to work with peers so they get an idea about what their level of understanding is and how what their strengths are as a problem solver, and also work at this idea of monitoring and controlling their mental processing. So a typical ESP 2-hour session, of course, they're very fluid, so it's hard to talk about a typical one, but I tried to give a graphical representation here. Students spend most of their time in collaboration. They also spend time at the board, okay? A typical ESP session may begin with board work, where students have a task that they go up to the board and they work and they critique each other's work. There's also some individual work in which they need to think about things before they start collaborating. And then there's some instructor-led discussion, which there may be points in which there needs to be some closure at the end of class, or times of intervention during the actual session. So let's look at this ESP task, okay? So it says, for the functions f and g shown, list at least 5 mathematical questions about f and g or both, okay? At least 2 of your questions should involve recent ideas from class about limits and continuity. So let me give you about a minute to jot down your own questions. Okay, so how would I take this back to some of the ideas about inquiry? I think this borders on open inquiry, in that the students are presented this task. Yes, it's I've drawn the graphs there, but then they're having to generate the questions. And then in the second part of this, they're also asked to answer the questions they posed, and then to list any surprises or interesting mathematical outcomes they encountered in answering the questions they posed, and explain, okay? So the idea then is that they're generating the questions, and then they're examining their work, taking the time to do some metacognition, to think about their solutions, think about their thinking. The version 2 of this task, if we wanted to scaffold it a little bit more, or make sure that some important points came out, because if the students look at particular limits that involve the sum, the product, the quotient, and the composition of the 2 functions, and they're looking at examining this just visually, right? So we're pulling in this visual representation. What can they say about it? So there are certain points there where they can say something about it, and others, one would be hard pressed to say, okay, well, can you definitively say that the graph goes through that point or not? Here, then, this would be a little bit more of a guided inquiry question, and to get students to move towards some of the ideas that the instructor would like them to make sure that they encounter. So they have to answer their questions, and then think, and then talk about any interesting mathematical outcomes and explain. Version 3 of this task does a little bit more scaffolding, in that one can come up with the questions for the students, right? Which limits you actually want them to look at. But then in an ESP setting, you see that the students actually do have to grapple with some of their misconceptions and some of the ideas that they have about when can they tell that the limit of the product is the product of the limits? When can they tell that the limit of a sum is the sum of the limits? And what are the conditions, and how do they understand, and how to understand those results? So, for instance, one might include this limit, which takes the students some time to. Typically they'll say that it doesn't exist, right? And then they'll have to take some time. You say, okay, well, why, and how would you, what kinds of things did you try? And you can go through and scaffold a little bit with them, or try to get them to answer their own question. In Arlington, we have a project funded by the NSF Science Talent Expansion Program grant, which allowed us to start an Arlington Emerging Scholars Program 2 years ago. And that effort is in chemistry, pre-calculus, and calculus courses for engineering, chemistry, physics, and math majors. And that ARC program is restricted to those students in an effort to retain them in those majors or in the permutation of those. The Arlington ESP model deviates from the usual model in that our recruitment strategies, we try to recruit students who are at risk that we have determined that are possibly at risk of failing calculus. And we have, even in our second semester of calculus, taken students who failed first semester calculus and put them in an emerging scholar setting for calculus. And even though in terms of the research in ESPs and in that model they've always focused on students who thought of themselves as academically capable, and although there can be criticisms of skimming from the top, that's not quite the situation. But in our program, that certainly isn't the case. Our recruitment strategies are very different because the goal is this retention of these students into these majors, but from a sense of being able to pass calculus, not necessarily to get an A. So our results so far in our courses, I'm not sure you can see that table. I apologize, it's kind of small. You see that in a pre-calculus course that we've had ESP in for 2 semesters, we had about a 56% pass rate for ESP students compared to a 35% pass rate for students in the same lecture. And the drop rate was about a third less. If you look in our calculus course, which is Math 1426, if you can see the table, we have seen that our students who are in ESP in Calculus 1, starting in this is all aggregate data, the 75% of them have been able to pass calculus compared to those in the regular sections. 50% have been or passed calculus. If you look at our drop rates, the drop rates are also quite compelling in that only 5% of the students in Math 14 in the Calculus 1 that have been in ESP and Calculus 1 have dropped ESP compared to about a 22 to 24% drop rate in the other sections. Similar kind of result in Calculus 2, which is our Math 24-25. This is surprising, particularly if you pull out our calculus data for the spring, the spring is typically a weaker class where we have our failures in calculus. Last year, if I pull that data out, we had students who made the drop DFW rate in calculus that year was about 75%. So we only had about 25% of our students, it was very low, pass calculus. But the ESP students pass at a rate of about 70%. So it's quite surprising. Something about the inquiry that they're doing in the classroom is working. We're not quite sure what it is yet, but I think that this is a nice case or an example of how we're able to take students who are struggling and they're in an inquiry environment, but able then to do well compared to their peers. What do students say about emerging scholars or their Arlington Emerging Scholars? Says yes. So would you recommend A-ESP to a friend? Yes, it gave me time to learn math with others. Everyone had a chance to teach and learn. Okay. So if we think about what inquiry is and we think about our metacognition, this student hit some of these ideas just in their comment. Everyone had a chance to teach and to learn. What part of ESP had the biggest impact for them? Of course, there's that affective factor, or the friendships and camaraderie with people who take the class seriously. So it hit the goals of ESP, but it also has this, hits the goal of yesterday, I believe, in Lee's talk, when she talked about the MORE method, where you care about your students and you respect your students and you have this community. So there's this community going on. Also, the student says, it goes on to say, and the observed difficulties they may have. So that this relates to the metacognition, in which the students are able to make an assessment about where they fit into a bigger picture. It made it easier by improving my study habits. So somehow, being acculturated into that community, they were able to improve their idea about what studying math meant. Working in groups to bounce off each other. So this idea of collaboration, being able to collaborate with a neighbor and being able to take ideas and build on them, and then also discover their weaknesses and discover their strengths. So this relates back to some of the ideas I talked about earlier, in that if we're speaking about metacognition, you want to be able to be aware of how well you have a good way to assess how well you understand the material, but also know yourself as a problem solver. Just from these few examples that I've given, I hope that you can see that I believe that the key components of ESP overlap significantly with the key components of inquiry-based learning and what we know about how students learn. And are there any questions? Thank you.
I'm curious about how much of what you're doing now with the ESP program is through the STEP grant. Is that correct? Mm-hmm. And are you, I mean, as part of this, you must be thinking about how to institutionalize that. Like, what will happen at the end of the grant period to the program, and how are you going to manage continuing what's happening, the positive impacts that's happening now?
One of the pressures in the university, of course, is to serve more students. And we are experimenting with that next semester. We're going to have slightly larger sections and try to reach more students with fewer TAs, also to incorporate undergraduates in the effort. The institution is very much interested in, given our data, the institution is interested in trying to maintain it as long as it's not going to be cost prohibitive, right? The grant has allowed the luxury of being able to implement it, and we are brainstorming on how to institutionalize it. In particular, our institution is very much as many are, but we have one of our goals, of course, is to increase our retention rates because they're quite low.
I was just wondering if you could quickly share any problem resources that you know about, if someone wanted to do some lighter version of this in discussion sections.
Say it again?
Just resources for problems that students can work.
So there's a database for instructors. There's a database that Eric Sue put together and I worked on, and he took a whole bunch of problems from old worksheets that I had written a long time ago, and that's online. It's called the Better File Cabinet. Then any resources that we have, we'd be willing to share. So I can, if you get in contact with me, I can point you in the right places.
Do you have a minute to answer another question?
I believe it. Go ahead. I have 4 minutes. Yes.
Oh, okay, quickly then. I was wondering if the students pay more tuition fees for these courses, or the faculty gets more credit hours to teach those courses. How do you convince the students that you got to meet more time to work on this than the traditional students? And do you have any resistance to that kind of thing?
Yes, we do. So that's a good question. There's resistance initially when we started the program, but then students quickly saw the results they were getting from being in this environment. And pre-calculus is a little bit more challenging because that group has its own kind of life. So it's been more challenging in the pre-calculus group to get them to convince them that this is a good thing, right? However, this past spring, our sections were oversubscribed. We couldn't. The students who wanted to get in couldn't get in, and that's because word of mouth has gotten around that this is a worthwhile endeavor and something that actually does help them do better in calculus. So one of the recruitment strategies initially was to call students and to send notes and to explain to them what the research literature says about, or what results have been were already existing about how students do that participate in these kinds of programs. And then now the word of mouth has gotten out, so it's a little easier to recruit for the courses. Say it again.
Do they pay extra tuition, more tuition?
No.
Okay.
At our institution, we do not have them pay extra tuition. It's just an extra 4-hour lab that is appended to their calculus section. And the grant allows us to pay the TA that does that. So. Yes, sir.
I noticed that you mentioned self-assessment, students' ability to assess their own work. It reminds me that many, many times in my career I've had students who have made very, very poor grades on a test come to my office and they're astonished. They say, but I understand this material. Or students who have done poorly consistently on homework or tests who somehow think they're doing okay. Do you have any insight into this phenomenon of students being completely out of touch with how poorly they're doing?
I'm not sure I have any more insight than anyone else, but
Okay.
That's a very typical thing for in terms of their development as a learner, right? That they don't have a good mechanism for judging how well they are taking in the material and learning the material. And some of these methods, right, having students work collaboratively and having them in an environment like this helps mitigate some of that.